All right, we may have done this a little bit in the past. Let's see what they've got for us. All right. So the first idea is something called theoretical probability. Okay. Theoretical. And then the other, its counterpoint would be the experimental. Okay. There's two types of probabilities. Theoretical is what you would expect. And experimental is what you actually get. Like, for example, the probability of rolling ahead in a coin toss, right? Getting ahead is 1/2, right? Is half. So for example, if you tossed a coin 10 times, how many heads would you expect? 5, right? Yeah. Half the time. This basically means half the time you get a head and the other half you get a tail, yeah? So that would be the theoretical probability. This is what you expect. But then in reality, things could be different. You've rolled it, you've tossed it 10 times. You could maybe get 8 heads and 2 tails, right? So these will be different in real life. They could be the same, but they may also be different. But the best part about this is that the more number of trials that you do, this one we only did it 10 times, but let's say we do this 10,000 times, okay? The probability here right now is head is 4/5 and tail is 2/10, which is 1/5. The more number of trials you do, your experimental probability goes closer and closer to the theoretical probability. Okay, but it's not really feasible to do it 10,000 times. But if you were to do it, it's going to get closer and closer to what you would expect. But in a smaller number of trials, it will be different, what you expect and what you get. Let's see if we can do some questions. Something like this. Is there 1 and 2? No, there's not. So this one is a dice. So a dice has how many faces?
6.
6, right? It's basically a cube. Calculate the theoretical probability of getting a 6. P of 6 means that you roll a 6. When you roll a dice, you get a 6. What do you think?
Isn't it just 1 out of 6?
Yeah, exactly. It's just 1 out of 6. B, rolling an even number.
3 out of 6.
Right. Can we reduce 3 out of 6?
1/2.
1/2, yeah. The probability of less than 3.
Just 2.
So 2 out of 6, right? Which is 1 out of 3. Yeah. So this means you have 33% chance, or a third of a chance, to get a number that's less than 3, which would be 1 and 2, right? So that was a cube. Let's look at these. What's this question saying? So this person has spun the spinner 80 times, right? Look at this. There's 10 numbers. What's the probability that you get a single number? Like, what's the probability you land on a 2 or a 3 or a 4? If you rolled it 80 times. So each thing has a probability of 1/10, yeah? There's 10 total number and each thing occupies 1 space. So it's 1 out of 10, yeah? Every 10 times you get 1. Every 10 times you get a 2. Every 10 times you get 1, 3. Every 10 times you get 1, 4. Do you get that? So the expected value in 80 times would be what for each number? They will all be the same.
8.
8, right? So you're expecting to get 8 of each. That's the theoretical probability, right? But the experimental probability this person's recorded doesn't look like it's the same. It's pretty different, right? 9 had the highest number of occurrences at 14. So these would be the experimental probabilities. Let's look at the questions. The experimental probability of spinning a 3 is 8 out of 10 or 1 out of 10. Which numbers had greater experimental probabilities?
9.
Yeah, 9 is one of them. Yeah, there's more than one. So basically, actually, no, you're right. I'm looking at the wrong thing. 8, you're right. There's only 9. Only 9 had more, everything else had less. B, what's the theoretical probability of spinning each number? It's kind of given in the question. It's 1/10, yeah?
Mm-hmm.
Because there's 10 numbers and you can only roll one at a time. This one says calculate the theoretical probability. The first one is a quarter, yeah? What's the probability of rolling a head or a tail? That's just a half, right?
1/2.
Yeah. What about for this one? For this pie chart looking thing?
1/5.
Yeah. What about this one? How many faces does this have? Looks like that's a triangular pyramid.
Just 4.
Just 4, right? So what's the probability you roll each face?
1/4.
Yep, 1/4. Let's try doing these ones. The card ones are always a little bit trickier. I'll tell you this much. In a deck of cards, yeah, that just means a packet of cards. There's 52 cards, okay?
Mm-hmm.
And each suit has 13 cards. So you'd get 13 diamonds, 13 hearts, 13 clubs, and 13 spades. Let's look at C. What's the probability of drawing a black card out of a deck of cards?
26 out of 52.
All right, 26 out of 52. And you can even reduce that, right? That will just be 1/2. So half the time you'll draw a black card and half the time you'll draw a red card, yeah?
Mm-hmm.
What about this one? Drawing a red card less than 9. So how many cards do we have in each suit?
13.
How many do we have that are less than 9?
8.
Right, 8, right? So in each suit we have 8 and we have 4 suits. So there's gonna be 32 cards that are less than 9 out of 52, yeah, like that.
Mm-hmm.
I can reduce this to 16/26, right?
Mm-hmm.
8/13, there we go. Cool. 8 out of
Mm-hmm.
13. Let's look at this one. So now this one's a 12-sided dice. And this person rolled it 48 times. And these are her experimental probabilities. If you roll it 40, what's the probability of each number? If you roll it once?
1/12.
1 out of 12, right? So if you roll it 48 times, how many rolls do you expect of each number?
Like 4.
4, exactly. So each number you'd expect it to roll 4 times, okay? So that's the question. Which experimental probability matches the theoretical probability exactly? So odd number, there should have been half of them, right? It should have been 24 over 48, yeah?
Mm-hmm.
So that's out. Greater than 8, how many numbers are greater than 8? 9, 10, 11, 12, right?
Uh-huh.
So there are 4 greater than 8. And we know this, so each number should come up 4 times. So this is 16 over 48. This is true. What about P9?
Okay.
Is that true?
No.
No, right? It should have been 4 out of 48, right?
Mm-hmm.
Out of 48 times, you get a 9 4 times. Which experimental probability is the furthest from theoretical? So you're basically just comparing these numbers. Which one's the furthest away? Which also means if you subtract them, which one will give you the biggest number?
The last one?
Yeah, the last one would be the furthest away. Yeah. And this one's also pretty straightforward. There are 10 red marbles and 6 green in a bag. So how many total marbles are there?
16.
Yeah. So there's 6 green, 10 red, so there's 16 total. Alex will choose one marble without looking, calculate these probabilities. Getting a green marble.
6 out of
6 out of what?
16.
All right, and that's the same thing as 3 out of 8. Getting a purple marble.
0.
0, yeah. Red or green?
Like 16 over 16.
Right, which is also 1, yeah?
Mm-hmm.
This means you get 100%, there's a 100% chance, or it's guaranteed to get either a red or a green. All right, place 6 blue blocks, 4 red and 2 green in a bag. Well, we don't have any blocks to work with, but we can work with them on paper. 4 red, 2 green. How many total?
12.
12, right? What's the probability of getting a blue marble or block? Which is also denoted as P of B, okay?
6 out of 12.
Right, 6 out of 12, and you reduce it to 1 over 2. What about red?
4 out of 12.
4 out of 12, exactly. That's 1/3. What about green?
2 out of 12.
2 out of 12. What does that reduce to?
1 over 6.
1 over 6, exactly. These are just experimental. We could do them, but when you do them, it won't be the same, okay? Because there's not enough number of trials. There's a probability that it's going to be exactly as we expected, but that is highly unlikely. Let's see what else is there. Okay, this one's a little bit interesting. So this person says that the probability of catching a cold is 1 out of 2 because there's only 2 possible outcomes. Is he correct?
I guess.
So what he's saying is basically every day you go up or you get up and go out, there's a 50% chance you get a cold, yeah? But we know this is not the case, right? Are you sick half of the year? No, no one's sick half of
No.
the year. So this is not true. So why is this not true? Because there's more than 2 outcomes, right? Or there are other factors that affect you getting sick. There's a million possible things that can affect you getting sick or not. So no, this is just a very black and white way of thinking, and unfortunately for him, that is not true. If this were true, if this were to be true, then yeah, we would probably, I don't know, go extinct, because everyone's always sick. And when everyone's always sick, even the cold, it kind of mutates the virus, the cold virus. So that would not be fun for anyone involved. This one's a nice question. Suppose that you toss a coin and then you roll a 6-sided dice. What is the probability of getting heads and an even number? A little bit difficult question. To do this, now if you look at this, there's multiple events happening. First, you're rolling a coin, right? Not rolling, you're tossing a coin, yeah? And then you roll a dice. So there's 2 independent events happening, right? 2 independent events. So the best way to approach a problem like this is to draw something called a tree diagram. Now, what does that look like? Let's look at this. So this is event 1, right? We toss the coin, yeah? What are the outcomes when you toss the coin?
Heads or tails?
Heads or tails, right? So that's event 1. And then event 2 would be rolling a dice, right? So what that means is it's dependent. So either you first get a heads and then you roll a dice, right? But the outcomes will be the same. You either get 1, 2, 3, 4, 5, 6, or you roll a tail and then you get 6 different options, right? 1, 2, 3, 4, 5, 6, correct? Like this. So this is called a tree diagram. Now, what's the probability of tossing a head?
Half.
Half, right? Tails is half as well. What about here? What's the probability of getting individual numbers when you roll a dice?
1/6.
Yeah, 1/6, 1/6. So now let's see what they want. What's the probability of getting a head and an even number? Yeah. So that
3.
means, no, it's a little bit more complicated than that. So you can either get a head and a 2, yeah? You can get head and a 4. You can get head and a 6, yeah? That's it. That's it. So how do you get head and a 2? So what this means is you have to kind of go through the branches of the tree. You first go from starting point to H, that's 1/2, right? And then you go from H to 2. And we know this probability is 1/6 for everything here on the second tree. Yeah? So like that. That'll be 1/12. You see? Head 4 will be the exact same thing. Head 6 would be the exact same thing. Those are the 3 possibilities, right? And then you add them up. So what's 1/12 plus 1/12 plus 1/12?
3/12.
Yeah, 3/12, which is the same thing as 1/4. So you have a 25% chance, or 1/4 chance of this happening. You get a head as well as an even number. Okay.
Okay.
Look at B. What is the probability of not getting head and an even number? So the opposite of this. We don't want heads. We also don't want even numbers.
Wouldn't it be the same?
No, it would not be the same, because there's more of what we did not include, right? So we did not include this. So there's already 3 from the top. Yeah. 1, 3, 5. And then there's the whole bunch down here. So it's going to be more than that. In fact, to do this, you see not getting, yeah? Not getting, you can just do 1 minus getting. Just take it away from 1. This was the one of getting that, right? So you can just do, for part B, you can just do 1 minus getting, which just means 1 minus 1/4. That would be 3/4, like that. So there's a 75% chance you don't get a head and an even number. Or 3 out of 4. Okay. Let's look at this. There's another tree diagram question. Or this one actually says list, but to get the list, you first have to come up with the tree diagram. I guess you really don't. Let's do that anyways, because I think that's the most easiest way to do this. When you roll a dice, what are the possibilities?
Anything out of 6?
Yeah, so there's 6 possibilities, right?
Mm-hmm.
You get 1, 2, 3, 4, 5, 6. And then you're gonna spin a roulette that has 4 different colors. So everything has 4, right? From here,
Mm-hmm.
you see we built. So the question is, how many total possibilities are there? What do you think? So you have 6 possibilities from the first, 4 from the second, yeah?
So 24.
There's 24 total possibilities, okay? 24 total. Let's look at A. The probability of getting 3 and yellow. So that means you go up here 3, right?
Mm-hmm.
And then you go up here yellow. There's only 1, yeah?
Mm-hmm.
So you can do 1 out of 24. So that's one way of thinking it. The other way of thinking it is this. To get a 3, the probability is 1/6. And to get a yellow, the probability is 1 out of 4, right? Independently.
Mm-hmm.
That gives you 1 out of 24 as well. Okay?
Okay.
B, anything except 3 and yellow. So we want everything except 3 and yellow.
23 out of 24.
Yeah, good, 22. We just take away this from a 1. C, number that's greater than 3 and purple. So we're looking for 4 purple, 5 purple, 6 purple. What do you think?
Is it 3 over 24?
Yes, it is. It's 3 out of 24, which reduces to 1 out of 12, okay?
Mm-hmm.
Easy as that. Here's a biology question. Genetics. Calculate the probability of having 3 boys in a family with 3 children. So I can look at this. This is your first child. What's the probability? What's the possibilities here?
A girl or a boy?
Yeah, exactly. Girl, boy, right? And then this kind of builds up. Girl, boy, yeah? And then this kind of builds up as a girl, boy. And then again, this is a tree diagram. GB, GB. So how many possibilities are there? There's 8. Right? If you look at this, here, let me write down the letters. You can either get a GGG from the top branch. See that?
Mm-hmm.
Or you could get GGB, right? Or you can get GBG and like that, okay? And if you do this, you'll see that there's gonna be 8 of them. In fact, you can just count the final, this row here, this column. There's 8 total possibilities, all right?
Okay.
And it says having 3 boys. 3 boys means B, B, and B. What's the probability?
Is it just 1?
Yeah, it's just 1 out of 8. 12.5%, that is. Cool.
Mm-hmm.
Let's try this one. Deanna and Carol are playing a game. They roll a die twice. Die is just a plural form of dice. And add the numbers they roll. A sum of 5 scores a point. So they're rolling 2 dices, okay, or 2 die. You can say this is dice 1, and this is dice 2, okay?
Mm-hmm.
So in dice 1, you can get 1, 2, 3, 4, 5, 6, and same thing on the other dice, right? It doesn't change. This is not a abnormal. This is just a normal playing dice. So you can get something like this, yeah?
Mm-hmm.
Now, when does it add up to 5? Which two numbers should add up to get a 5?
3 and 2.
Exactly, 3 and 2. So this is one of the possibilities, right? What else?
4 and 1.
Yeah, 4 and 1. And notice there's 2 4 and 1s. You can either get a 4 on the first dice, 1 on the second, or you can get 4 on the second dice and get 1 on the first. Yeah.
Mm-hmm.
And there's also 3 2. So you can either get a 3 on the first and 2 on the second dice, or you can do vice versa, right? You can get a 2 on the first and 3. That's why. The next question will be, what's the sample space here? How many total possibilities are there? So when you get independent things, just multiply them, right? For the 3 boys question, we did 2 times 2 times 2 to get an 8. In the other, the dice and the spinner question, we did 6 times 4 to get a 24. In this, there's 6 possibilities on the first, yeah? 6 on the second, so there's total 36 possibilities. Okay?
Mm-hmm.
Look at A. What's the probability of rolling a sum of 5?
Is it 4?
Yeah, it is 4. What does that reduce to? 4 out of 36.
Um, 1/9.
Yeah, that is right. 1/9. B. Deanna rolled a sum of 5 on her first turn. List the different ways she could have done this. It's already listed up there. She can either get a 1 on the first, 4 on the second, yeah?
Mm-hmm.
Or flipped 4 on the first, 1 on the second. Or she can do 3 2, 3 first, 2 second, or 2 3. So there's 4 different ways to get a sum of 5, okay?
Mm-hmm.
Look at C. What's the probability that when she rolled a sum of 5, the number on the first roll was greater than the number on the second? It's basically asking
Just 2.
probability, not the number of times it happens, the probability. It is 2, but that's not the probability. Probability will strictly be between 0 and 1, cannot be greater than 1 or less than 0. So there's 4 total ways she can roll a 5, yeah?
Mm-hmm.
What goes in the denominator, and how many, in how many ways is the first number greater than the second? You can either have 4 1 or 3 2, yeah? So there's
Mm-hmm.
like that. You say 2 out of 4 or 1 out of 2. There's a 50% chance that the number on the first roll was greater than the number on the second roll.
Okay.
Does your brother go to school?
No. He goes to daycare.
All right, let's look at this. What is the theoretical probability of each event? Drawing a queen from a standard deck of 52 cards. I'll give you a hint, all right? Every suit has its own queen. So there's a queen of diamonds, there's a queen of hearts, there's a queen of spades, and there's a queen of clubs.
So 4.
4 out of what?
52.
Exactly, and that's the same thing as 1 out of 13, all right?
Mm-hmm.
Rolling a 1 using a standard die.
1 out of 6.
Right. Spinning a 9 with this spinner.
0.
0, good. Drawing a black card from a standard deck of 52 cards.
26.
Yeah. 26 out of 52 though, right?
Mm-hmm.
Asking for the probability. So that's gonna be 1/2 as the final answer. All right.
Mm-hmm.
All right, this one says, so there's options, and each of those options is the right answer to the question. So what's going on here? So they spun this 36 times. Choose the fraction that matches each probability. The theoretical probability of spinning an odd number.
Um, 5 out of 9.
Yeah, 5 out of 9. The theoretical probability of spinning purple.
1 out of 9.
Right. An unexpected experimental probability of spinning blue.
What does that mean?
That means it's like you didn't expect that to happen. So it's very, very far off from the theoretical probability. I mean, there's only 2 options left, right? Let's do D first, and I guess we can come back to C. An experimental probability of spinning an even number.
4 out of 9.
Is that an option? 1, 2, 3, 4. Oh, it says experimental, all right? Yeah.
Oh.
So this could be 9 out of 18, whatever. This could be 14 out of 18. So both of these are experimental, right? They're gonna change each time, but A and B is the theoretical. It'll stay the same. Jeff rolled a die 600 times. Mary rolled it 6 times. In which case is it more likely that the experimental probability of rolling a 1 was 1/6?
Rolling it 600 times.
Yeah, the more you roll it, the closer it goes to the experimental probability. Or sorry, the theoretical probability. Number of trials won't help you. You might get unexpected results. This one says, suppose you're going to roll a 4-sided die with a 6-sided die. Create a T diagram. All right, so this is what happens in this. Let's say in the first, there's only 4 possibilities, right? In the first one, you go 1, 2, 3, or 4, yeah? And then you're rolling a 6-sided die. So you could either get 1, 1, 1, 2, 1, 3, 1, 4, like this, okay? 1, 5, 1, 6. Same thing with the 2, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. You see what the question? How many total possibilities are there?
Um, 24.
Yeah, there's 24 possibilities. Look at the question. Calculate the theoretical probability of a sum of 2. How many of these would we get a sum of 2?
4.
Where are you getting 4 from? So we know the total possibilities are 24, yeah?
Mm-hmm.
The sum of this is 2. There's only one, right?
Oh, okay.
Everything else would be greater than 2. So the sum of 2 is only 1 out of 24, okay?
Mm-hmm.
Sum of 3 and 4. So 3, 4, right? That's done there. 3, 4, yeah? 4 can't have a 3 with the third. The fourth one can't have a 3 nor a 4. So how many outcomes are there that results in getting a sum of 3 or 4?
5,
5 out of
24.
24, right? The third one, sum of neither 3 nor 4.
19 over 24.
Yeah, good. 19 over 24, okay? Now let me tell you some statistics lingo. This thing, sum of neither, okay? For example, you have some event A, okay? Let's say the probability of A is 1 over 5, yeah?
Mm-hmm.
What's the probability of not getting A?
4 over 5.
Yeah, 4 over 5. Now, the probability of not getting A or no A, that is denoted like this, P of A bar, okay? See the bar up
Mm-hmm.
there? That means no A, not getting an A, or exclude A, okay? Everything but A. That's what the bar
Okay.
means. And the word for this is the complement of A.
Mm-hmm.
Let me show this to you visually. This box represents all the possible probabilities, okay?
Uh-huh.
Our circle in the middle is event A, right? Our
Mm-hmm.
event A, complement A bar is this, everything that's outside the circle, okay? Everything outside the circle is A bar, not A. Cool?
Uh-huh.
If A is whatever, 1 out of 5th, A bar would be 4 out of 5th. So that's also called the complement event.
Okay.
Suppose you roll a 12-sided die and you also spin the spinner. Which is more likely, rolling an even number and spinning A, or rolling, okay, so this one's gonna be a little bit tricky. Let me write down the sample space, okay? So 12-sided die means either you get a 1, yeah? You can get
Mm-hmm.
1A, 1B, 1C, 2A, 2B, 2C, you see that?
Mm-hmm.
All the way down to 12A, 12B, 12C. How many total possibilities are there?
36.
Yeah, there's total 36 possibilities. Which is more likely? Rolling an even number and spinning A. So how many are there? What's the probability of this happening? Even number and A. So that means 2A, 4A, 6A, 8A, 10A, and 12A, right?
Mm-hmm.
So how many are there? There's 6, right?
Mm-hmm.
If you just count them, even number with A, 1, 2, 3, 4, 5, 6. So it's 6 out of 36. That's 1 out of 6, right?
Uh-huh.
What about this one? Rolling a number that is not a multiple of 3. So you can either have 1 or 2, yeah? Actually, you can also have 4. No, there's not just 1 and 2. So we know the answer to the first thing is 1 out of 6. Now let's look at the second one. Multiple of 3 and not spinning C. So what does that mean? That means 1B, 1A, yeah? can't have C, correct? 2A, 2B. And 3 is out because it's a multiple of 3. Then 4A, 4B, 5A, 5B, 6 is out, 7A, 7B. What's the next one? Not a multiple of 3 and not spinning C.
8A and 8B.
Right, 8A, 8B. And then 9 is out. We have 10A, 10B, and then 11A, 11B, and 12 is out because that's a multiple of 3. Yeah. How many are there? 1, 2, 3, 4, 5, 6, 7, 8. So there's 16 possibilities here, you see? So that's 8 out of 18, and that's 4 out of 9. Which is bigger, 16 out of 16 or 6 out of 36? Which is bigger?
The second one?
6 out of 36? No, when the denominators are the same, just compare the numerator. This one is bigger.
Oh, okay.
Okay, 16. So you're more likely to roll a number that is not 3 and not spin C rather than rolling an even number with an A, okay? This thing that we just made was a list, yeah? Let's see what else they got for us. Kaylee threw 3 darts in the target and hit 3 different colors. In how many ways can her score be greater than 30? Pretty difficult question. So there's 4 numbers, right? 20, 10, 5, and 1.
And 4 colors?
Yeah, and she's only throwing it 3 times, right? So we have 3 events, yeah? So look at this. We can either get, let's say in the first one, she hits a 1, okay? We're gonna have to draw a tree diagram here. So 1, and then you can either get a 1, 5, right? 1, 10, 1, 20, yeah? 1, 5, 10, 1, 20. So the 5, 10, and 20 represents the second throw, yeah? But you could also get 1, 1, right? In the second one, you could also get 1. What does that look like visually? Looks something like this. So you land on a 1 first, and then on the second one, you can either land on 1, 5, 10, 20, yeah? And then you keep going 1, 5, 10, 20 on the third one, right? And then you got to do this 4 times for 4 different starting values. That's pretty tedious. Yeah, that's what I thought. And then you just add them up and you make a chart, okay? This will take some time, but this is the way to do this. See, there's no easy way to do this. You kind of have to brute force your way, okay?
Okay.
Let's try doing something else that's a little bit easier, so we don't have to brute force. I mean, we could have done that. It's just gonna take a long time. It takes like 10 minutes. Let's try this one. John has 4 jobs, okay? For variety, he chooses slips of paper from a jar each morning to decide in which order will he do the jobs. What is a probability that John would unload the dishwasher after taking out the garbage? Any ideas on how to approach this at all?
Could you draw it out?
Right, you could, right? So how would you even draw this out? Step 1, how many total outcomes are there? So there's 4 jobs to do, yeah?
Mm-hmm.
How many slips of paper does he take out from the jar every morning?
4.
4, right? So there's total 16, okay?
Mm-hmm.
Now the question is, out of the 16, how many times would dishwasher come after garbage? Any ideas?
No.
So you can either have like bed, dog, D, G, right? Maybe I
Mhm.
should use a different one for dishwasher. I'll just use W. So B, D, W, G, yeah?
Mhm.
What do we need? We need the dishwasher after the garbage. Or you could have B, D, G, W, yeah?
Mhm.
Or you could have B, G, W, D, or you could have B, W, G, D. Like that, okay?
Mhm.
So each thing, how many times is G beating, sorry, how many times is W beating G? 1, 2, right?
Uh-huh.
So whichever one you start off with, in every event, W is beating G twice. There's 4 events, so it's going to be 8 out of 16.
Okay.
8 for 4 times 2. Oh. So these ones are a little bit trickier. Not a fan of these.
Me neither.
Because it takes a long time. Let me see, that one we can ignore. They're all the same questions. Let's try this one, these ones. This one says, which model could be used to simulate the experimental probability shown below? So we know the probability of this is 1/2, 1/6. This looks like a calendar, 1, 3, 6, 5. This is 1/8, okay?
Mhm.
Look at A, B, C, and D. Which option has a probability of half?
C.
C, right? So C is gonna be A. What about 1/6?
A.
A, right? There we go, B. What about look at option B? Which one would that be?
Um.
I mean, D is the 8th box, so D must be C. That means B is this calendar one. Okay.
Mhm.
Okay, look at this. It says, which spinner could be used to simulate the experimental probability here? You have volunteered to help out one day at a week-long summer festival. What is the probability that it'll be Wednesday? It's basically
1/7.
asking, yeah, 1/7. Which diagram represents a probability of 1/7, A, B, or C?
C.
Yeah, that's right, C. In a game of chance that is played in pairs, let me pull this. Again, these are from the diagram. That is played in pairs, you can win, lose, or tie. So which one represents that probability? Which diagram?
A.
Yeah, A, because there's only 3 probabilities, right? Or there's 3 possibilities, which is also called the sample size. C must be B automatically, yeah?
Mhm.
C must by through the power of elimination. What about this one? You'll select only red jelly bean in a bag of 26 jelly beans. Oh, this is not a calendar. This is a pack of cards. This is a pack of cards. I thought it was like a calendar thing because it was so blurry. So that's a standard pack of cards. Okay, there's 52 cards in there. Let's look at option A. So again, the question is which diagram can we use for the probability? You'll select the only red jelly bean in a bag of 26 jelly beans.
B.
Right. B. You'll score 10 out of 10 on a true false quiz by guessing. So this one you kind of have to think. You can use A, yeah, you can use A, and you can say you get 10 heads out of 10 tosses. Okay. For A, actually, you could say something like this. You get 1 red card, yeah? Or you want 1 out of 26, so 2 out of 50, 2 out of 52. So you get 2 red cards from a standard deck of cards. Okay, so we kind of have to modify the options a little bit. Look at C. A family with 4 children has all girls. Which one can we use and modify a little bit?
A.
How would you explain it? You could roll a coin, right? You could toss a coin, yeah? And you can get all heads, right? That would simulate this, correct? Look at D. D must be B. I mean, 30% chance, looks like there's 3 red out of 10 total, so D is B, okay? So we're just kind of modifying the thing a little bit. All right, let's try doing this one. This one, I don't think you have to modify, but we'll see. A. 2 field hockey teams are equally matched. What is the probability that the same team will win all of the next 4 games they play? Which one can we use for that?
You could use A.
Yeah, you could use A and roll all 4 heads or 4 tails, yeah? Let's look at B. To qualify to win a trip to Orlando, you must guess the week of the trip. There is 52 cards in a deck. There's also 52 weeks in a year. Which one could we use?
D.
D, right? But what would you say? So we need a probability of 1 out of 52. Yeah? How can you modify D to get a probability? What would be an example of getting 1 out of 52 using D?
One specific card?
Yeah, 1 specific card, right? So you can get an ace of spades or a 3 of diamonds or something, right? Both of those have a probability of 1 out of 52. Look at C. There's a 30% chance of snow on the next 3 days. What is the probability of getting snow on one of these 3 days? This one's tricky, yeah? You can use C, okay? And you can say 30% chance means there's 10 here, so that's 3 out of 10, right? You can say a multiple of 3. Multiple of 3, because that's 3, 6, and 9, yeah?
Uh-huh.
So what is the probability that you get a multiple of 3? And that will resemble option C, because there's the probability of that is 3 out of 10. And that's what this is, right? 30% means 3 out of 10.
Mm-hmm.
You kind of get that?
I do.
It's a little bit tricky. The math is very simple here. Like just the pure mathematics, the algebra, whatever the arithmetic is very simple, but it kind of makes you think. That's the difficult part about probability. Okay.
Uh-huh.
Okay, we can pick it up next time.
All right. Thank you. Bye.
Bye-bye.